In the last video, we understand why we need Laplace transform. Now in this video, we define Laplace transform properly. So Laplace transform of a function ft is defined as integral from 0 to infinity e to the power minus st into ft dt. Now this right hand side term is in domain S. So we write it as f of S. Let's take some example. Suppose we want to find the Laplace of function ft equals to 1. So Laplace of f of t will be equal to integral from 0 to infinity e to the power minus st into ft dt. This is equals to integral from 0 to infinity minus st, ft is 1 dt. Now integration of e to the power minus st will become e to the power minus st upon minus s, and the limits will be 0 to infinity. This will become 1 upon minus 1 upon s, e to the power minus s into infinity minus e to the power minus s into 0. Now e to the power minus infinity will become 0 and e to the power 0 will become 1. Hence it becomes 1 upon s. So Laplace of 1 is equals to 1 upon s. Let's take another example. F of t equals to e to the power at. Now Laplace of ft is equals to integration from 0 to infinity e to the power minus st into ft dt. This will become integration from 0 to infinity e to the power minus st into e to the power at dt. Integration from 0 to infinity. We can write this term as e to the power minus of s minus at dt, and the integral will become minus 1 upon s minus a e to the power minus s minus a t, with limits from 0 to infinity. This become minus 1 upon s minus a. On putting infinity, e to the power infinity will minus infinity will become 0 and e to the power 0 will become 1, and this become 1 upon s minus a. After minus minus cancel each other. So Laplace of e to the power at is 1 minus s, 1 upon s minus a. Now let's see the Laplace transform for some common functions. These are very important in solving the problems of Laplace transforms. For function ft equals to 1, the Laplace transform will be 1 upon s. Just now we see that. Laplace transform of ft equals to t will become 1 upon s square. For t square, it will become 2 factorial upon s cube. In general term, for t to the power n, the Laplace transform will be n factorial upon s to the power n plus 1. Let's see some more functions. For cos omega t, the Laplace will be s upon s square plus omega square. For sin omega t, omega upon s square plus omega square. For cos hyperbolic omega t, the Laplace will be s upon s square minus omega square. And for sin hyperbolic omega t, it is omega upon s square minus omega square. So to remember this, you can see in cos omega t and sin omega t, the denominator term is s square plus omega square. In cos omega t, the numerator is s, and in sin omega t, the numerator is omega. Similar fashion, we can see in cos hyperbolic omega t and sin hyperbolic omega t. The numerator term is s and omega respectively, while the denominator term is s square minus omega square. Now let's define the Laplace of cos omega t. So in order to do that, we can either follow the basic approach, that is the integral one. We can solve the integration from 0 to infinity e to the power minus st into cos omega t dt. But it would be a lengthy approach. So instead we will break cos omega t into Euler's formula, that is 1 upon 2 times of e to the power I omega t plus e to the power minus I omega t. So Laplace of cos omega t will become 1 upon 2 Laplace of e to the power I omega t plus Laplace of e to the power minus I omega t. This will become 1 upon 2 1 upon s minus I omega. Since Laplace of e to the power at is 1 upon s minus a plus 1 upon s plus I omega. Solving the terms, we get s plus I omega plus s minus I omega, and in denominator we get s square minus I square omega square. These terms will cancel each other and we will get 1 upon 2 times of 2s upon s square plus omega square. Since I square is equals to 1, since I square is equals to minus 1, so the denominator term will become s square plus omega square. 2 cancel, and we will get Laplace of cos omega t as s upon s square plus omega square. Now let's look at the Laplace of cos hyperbolic at. So again we can break cos hyperbolic at as e to the power at plus e to the power minus at upon 2. So Laplace of cos hyperbolic at will be 1 by 2 Laplace of e to the power at plus Laplace of e to the power minus at. That is 1 by 2 1 by s minus a plus 1 by s plus a. This will become 1 by 2 2s upon s square minus a square. This is equals to s upon s square minus a square. Now in similar fashion, you can find the Laplace of sin omega t and Laplace of sine hyperbolic omega t. So you can break sine omega t as e to the power I omega t minus e to the power minus I omega t upon 2, and you can break sine hyperbolic omega t as e to the power omega t minus e to the power minus omega t upon 2. Laplace for 2t plus 8. So we can write this as Laplace of 2t plus Laplace of 8, that is 2 times Laplace of t plus 8 times Laplace of 1. Now Laplace of t is 1 upon s square and Laplace of 1 is 1 upon s. So this becomes 2 upon s square plus 8 by s. Let's see another question. So we have Laplace of cos square omega t. So here we can write cos square omega t as 1 plus cos 2 omega t upon 2. So Laplace of cos square omega t will become 1 by 2 times of Laplace of 1 plus Laplace of cos 2 omega t. This is equals to 1 by 2. Laplace of 1 is 1 upon s, and Laplace of cos 2 omega t will become s upon s square plus 2 omega square. That is 1 by 2, 1 by s plus s upon s square plus 4 omega square. Now we have to find the Laplace of 1.5 times sine 3t minus pi by 2. So we can write this as Laplace of 1.5 sine 3t minus Laplace of pi by 2. This will become 1.5 times Laplace of sine 3t minus pi by 2 times Laplace of 1. This will become 1.5 into 3 upon s square plus 3 square. Since Laplace of sine omega t is omega upon s square plus omega square, minus pi by 2 do 1 by s. This will become 4.5 times s square plus 9 minus pi upon 2s. Another question. Here we are given a function and we have to find the Laplace of that. Now this function f of t can be represented as k, where t lies from 0 to c. To find the Laplace of this function, we will use the basic integral formula of Laplace. It is 0 to infinity e to the power minus st into f of t dt. Now this becomes integration from 0 to c, since f is defined for 0 to c, e to the power minus st into k dt. This will become k times e to the power minus st upon minus s with limit from 0 to c. This will become k minus k upon s e to the power minus cs minus e to the power 0. This will become minus k upon s e to the power minus cs minus 1. Let's see another question. Here we are given the graph of f of t and we have to find the Laplace transform of that. Now we can see this function takes value from 0 to 1 and 1 to 2. So from 0 to 1, the distribution is like f of t is equals to t because x and y are equal. And from 1 to 2, the distribution is f of t is equals to 1. So we can write f of t as t, where t lies from 0 to 1, and 1 when t lies from 1 to 2. Now the Laplace of f of t will be equals to integration from 0 to infinity e to the power minus st into ft dt. This will be equal to integration from 0 to 1 e to the power minus st into t dt plus integration from 1 to 2 e to the power minus st into 1 dt. Now we have two terms. One is e to the power minus st into t dt and one is e to the power minus st into 1 dt. For the first function, we can solve it using integration by parts, where t will become our first function and e to the power minus st will become our second function. So it will be equals to t into integration of e to the power minus st with the limit from 0 to 1 minus integration from 0 to 1 differentiation of t into integration of e to the power minus st dt. And for the second function, it will become integration of e to the power minus st upon minus s with limit from 1 to 2. This will become minus 1 upon s t into e to the power minus st with limit 0 to 1 minus e to the power minus st upon minus s into minus s, that is s square, with limit from 0 to 1, and the second term will become minus 1 upon s e to the power minus 2s minus e to the power minus s. This will become minus 1 upon s e to the power minus s minus 0 minus 1 upon s square e to the power minus s minus e to the power 0 plus minus 1 upon s e to the power minus 2s minus e to the power minus s On solving, we will get minus e to the power minus s upon s minus e to the power minus s upon s square. E to the power 0 will be 1. So plus 1 upon s square plus e to the power minus 2s. It will be minus here upon s and plus e to the power minus s upon s. This term and this term cancel each other, and we will get minus of e to the power minus s upon s square plus 1 upon s square minus e to the power minus 2s upon s. This will be the answer.